Our objective today is to calculate the volume created by a solid of revolution by using the disk method. Here's the important thing. We're going to do another solid of revolution. For the next section, it's the same idea, but this one is using a disk, that one's using a washer. Here the important thing is the axis of rotation is one of the boundaries of the area you're rotating. That's what makes a disk work. One of the axis of rotation has to be a boundary of what you're rotating. So you have an area, you're spinning that area around. In order for the disk method to work, the axis of rotation has to be one of the boundaries, or it doesn't work. Okay? So, let's take a look at the function y equals x squared. Consider the region bounded by the function, the x-axis, and x equals 3. Okay? So, the idea is, I go, all right, I have this function. I have this, line x equals 3, and the x-axis. I'm going to take this area here, and I'm going to rotate it. I'm going to take that and spin it around the x-axis, thus creating that object. That's the idea. What is the volume of that object that I just created? That's what we're looking for here. Okay? I take that, spin around the x-axis, that's the volume you get. Whatever the object you get, we want to find that volume. Okay. Okay, now let's look at only one rectangle in our region rotating around the x-axis. The rectangle in this method will always be drawn perpendicular to the line we rotate around. This is important. Okay, the rectangle will always be drawn perpendicular to the axis of rotation. The rectangle is always perpendicular to the axis of rotation with this method.
What rectangle is it referring to?
That's where you'll see in the next picture. But that's one of the important thing is the rectangle we're going to draw, the object, the idea that we're rotating around is always perpendicular to the x-axis. Always. Or perpendicular to the axis of rotation. If we rotate it around a line this way, we're measuring the radius in this direction. If we're rotating around in this direction, we're going to measure it this direction. So if we're rotating around a horizontal axis, we're going to be doing it dx. If we rotate it around a vertical axis, we're going to be doing it dy. Okay. So this is what we're talking about. So if I take a rectangle, and that should, let's go back. Yeah. So if I go back here, so the idea is we take one rectangle and we spin that around. Okay, and when we spin that one rectangle around, we end up with that. It's our disc, our washer, or it's a cylinder, or our disc, right? Cylinder and a disc is the same thing. What's the difference between the cylinder and a disc? Cylinders tend to be tall and skinny, discs tend to be big and round and very short. But they're the same shape, just different proportions. Okay? But that's what we're doing. We're doing a disc. You take that, rotate it around, you get a disc. Okay. And actually, I don't need to erase. What is the volume of a cylinder? You need to know the volume of a cylinder. Okay, one of those things that you kind of need to know. And actually, you will be expected for some of the AP questions to know volume of a cylinder. Remember when we did related rates? Some of them were cylinders for some of the objects you were filling or draining. That one you're expected to know. You're not expected to know volumes of spheres or volumes of cones. If a cone is involved in the problem, the AP will give you the equation for the volume of a cone. They will give you the equation for anything to do with a sphere. The surface area or volume, they will give you that. They expect you to know this one. I expect you to know this one. So, this is also known as the banana model. If I want to find the volume of a banana, I slice it up. I get a bunch of little discs, right? Okay. Now I like this one here. This is the disc method. This is what we're doing here today. This is the concept of what we're doing. We're taking it, creating all these little discs, and adding them together. Here's the cool thing about what we do in this class. Is we are going to take really skinny, almost non-existing in width discs, and we're going to add them all together. We're going to take an infinite number of skinny discs and add them together because we're really awesome, and we can add an infinite number of things together. Because we're awesome. That's what we are in this class. And doing an integral is adding together an infinite number of objects. So we're going to add together an infinite number of disks, the volume of an infinite number of disks in here. Okay, so the disk method. So if we're looking at our original problem we were starting to talk about, okay, and we're finding this one here. Remember what we started with? Okay, that's the object. Our equation is y equals x squared, and we're going from 0 to 3. Okay, that's our original thing. We're spinning that around. That's how we get that object. And we have one rectangle in there. What is the height of that rectangle? Okay, the height of that rectangle is the function. It's the distance from the x-axis to the equation. It's the distance of that function. In this case, it's actually our radius, because what are we doing? We're rotating it around, getting a disk. So that distance there is our radius. Our distance is our function. Now that may change if we move things, but that's our distance. Okay. Our height of our disk, the width of the disk. Our height is the distance here from the beginning to the end. It's going from one x coordinate to the next x coordinate. In other words, our change of x. In other words, our delta x. In other words, dx. Which means that our formula for the disk method is that. The volume is the integral from A to B, one edge to the other edge, pi r squared h. R squared is f of x, h is dx, so it's pi f of x squared dx. Now, it's only f of x if the x-axis is our boundary of rotation. If the x-axis is on our boundary of rotation, it is not f of x. It changes accordingly. We will do some examples to change accordingly. We might be doing it around the y-axis, in which case it would be f of y. We'd write it as a function of y instead of a function of x. But we can rotate it around other lines, which means we have to figure out what the radius is accordingly. Drawing pictures and diagrams to find your radius in particular is extremely important. Okay, I cannot overemphasize doing that. To label them and do it. Okay. So let's do this. Let's find the volume of this object we've been talking about. So I'm taking this space here, rotating it around, and it's going to give me an object where a cross-section down the middle is going to look something like that. Our axis of rotation is down the center. There's one of our rectangles. Okay, what's our equation? What's our equation again? It's y equals x squared. So what's the radius? Our radius is x squared. Okay. So our volume is equal to the integral of pi times x squared dx. And we go from where to where? 0 to 3. Okay. Now, a couple of things. Okay. If you can, and please do, pull the pi out front. So my volume is equal to pi times the integral from 0 to 3 up x to the 4th dx. This question, if they were doing something like this, would most likely be on a non-calculated portion of the test, particularly if they give you numbers as easy as to look like this one. If they have it on a calculator portion of the test, they do mean things to like make you find points of intersection using your calculator and your solver menu, because it would never be 0 and 3. It would be something like 0.2568 and 5.24829. And the only way to find those points is to use your calculator, which is really and I am being sarcastic with that one. Okay. But if this is a hand one, and at this point you can do it by hand or do it using your calculator. So you would get pi times the antiderivative of x to the 4th is x to the 5th over 5, evaluated from 0 to 3. And if you work that out, you get 243 over 5 pi, I believe. I wrote down the problems to make sure I got this one right. Actually printed up a couple of notes. Yeah, 243 over 5 times pi. That's exact. If you multiply it times 3.1415926, you will have an approximation. I prefer exact numbers over approximations. However, on the test, I would take either one of them. Because you don't need to do the antiderivatives or anything like that by hand on this particular test coming up. On this test coming up, I'm looking for the equation. I'm looking for the answer. Give me the integral with the bounds and the function set up right and the constant of variation. When we start looking at AP practice questions, when they ask something like this, they will often say 1 point for the bounds and constant of integration, which means you get 1 point for the pi and the 0 and the 3. That's what they mean by the constant of integration, the pi. Okay? You get 1 point for having that and the correct bounds. Okay. Questions so far? It's not a horrible concept. Don't worry, it will get more difficult as we go through. Okay. Next one. Find the volume of a solid of revolution generating by revolving around the x-axis region in the first quadrant bounded by the x and y-axis and the ellipse 4x squared plus 9y equals 36. Oh, crap. So, what exactly is it asking for? Well, I can tell you exactly what it's asking for. It's asking you to draw a friggin' picture. X-axis, y-axis. The curve, 4x squared plus 9y squared equals 36. 4x squared plus 9y squared equals 36. Okay. And then what are you doing? You're revolving that around the x-axis, right? Well, the x-axis for each revolving around the x-axis. That's important. So this is our rectangle, which means our radius comes from that height there. But you have to understand what it's asking you to do. This is the shape you're trying to get. Okay, the front half of a football, so to speak. Well, it's not really an ellipse. That's closer to a rugby ball. Okay, so I need to have this distance here as a function of y. I can't use the equation I have. So what do I need to do? Yeah, I got to solve it for y. So subtract 4x squared from both sides. 9y squared equals 36 minus 4x squared. Divide both sides by 9. Y squared is equal to 4 minus 4/9 x squared. And then y equals the square root of 4 minus 4/9 x squared. And technically this is plus and minus. The plus is the upper half of the curve, the minus would be the lower half of the curve. Either one I actually could use. I could use either one of them, it doesn't really matter. Okay, but use the positive because why screw the negative if you don't need to? That's my philosophy. If you don't need to worry about the negative, don't worry about the negative. Okay. So that's my radius. That's what I'm dealing with. Okay, and what are my bounds? This one's easy. It goes from 0 here. Then I got to figure out what the other bound is. What the end point here is. So y would be 0, right? So at this point here, y is 0. When I put in 0 for y, put in 0 in here, I get 4x squared equals 36. X would be 3. And there you go. That's the integral you need to set up. Pi times the radius squared. So do you see where I get the equation there? Because if you take the square root of 4 minus 4/9 x squared and you square it, what do you get? 4 minus 4/9 x squared. Okay, that's the square root squared. That's where you get the parentheses. And then from there, you end up solving it out to get 8 pi. The key is figuring out what is your frickin' radius. That's the most important part and probably the most difficult. But if you draw a diagram, it really makes it so much easier. Draw a diagram. Draw the x and y axis. Make sure you know what the line you're rotating it around is. What are my functions that are involved? Draw them. It makes a difference. Okay? It'll often tell you your bounds. A word of caution. If this was in your textbook, this is not how your textbook would do it. Because they never do things the easy way when they have the chance to do the hard things in this particular section of your textbook. They like to use what is called the washer method. So they would do it dy and have something really complicated and nasty because I don't know why. This would be the easier of the two methods. So there's more than one method for solving. This is by far and away the easier one to do. But for some reason, your textbook would like to do it the hard way. Now, the answer would be the same in the end. So if you are checking the answer in the back of your textbook for your homework from tonight and from the next part we do, if they don't have an equation that looks like that, if they have an equation that starts out with 2 pi, ignore their work and just look at the answer. I'm telling you right now, if they have one that begins with 2 pi, that means they did the cylindrical shells method, and I'll demonstrate that to you at another time. We're not going to do it in here, but I will demonstrate it to you so you kind of understand what it is. It's not required for anything you need to do in AP. There's only certain times you absolutely have to use it, but your textbook uses it when they don't have to. So 90% of the time, they use it for everything. And they don't have to, but they do anyways. Okay, just warning you. Okay, so let's do this one. Find the volume of the solid revolution generated by rotating the region bounded by the line y equals 2x plus 3, the line x equals 3, the x-axis and y-axis about the x-axis in terms of pi. So, first step, draw a diagram. Draw those parts. Draw the line, draw the boundaries, sketch it out. Do that first before you do anything else. And please, on your paper, don't make it this stupid, teeny, tiny little drawing that you can't read anything that you label on it. Yes, many of you do that. I've been doing this for years. It drives me bonkers, especially when I go to graded tests. and I can't, it's this little tiny little thing. Draw big so you can label it and read your labels. And so somebody else doesn't have to get out a freaking magnifying glass to read your work. I don't want to do that. Okay, so we're not going to finish it, but before you continue on, X and Y axis, the line Y equals 2x plus 3, and the line X equals 3. This is the area of your rotation. And what are you doing? You're taking this and spinning it around to give you an object where that would be the bottom. So your radius is this distance here. Okay? Draw it in first. That's what we're doing. Okay? There's a name for this. I forgot what the name of this thing is. No, there's a particular, for that object. When you spin it around, there's a particular name for that. I forgot what it is. Okay? But that's what you're doing. So that's your first step, is to draw it, set that up. Figure out your radius, figure out your bounds, set up the equation. Okay. So let's finish this off here. So we have the integral of pi times our radius squared dx. Now we have to fill in, guys, now we have to fill in our blanks. What's our radius? 2x plus 3. It's easy because the x-axis is our boundary, so this distance here is our function, so it's 2x plus 3 squared. And then our bounds would be 0 to, and what does it say here? The x-axis, x equals 3. And then you work that out. And you can do antiderivatives on this, work it out, and you get 117 pi. It's actually not too bad. If you were doing this, if I were doing this by hand, square out the 2x plus 3, pull out the pi, do the antiderivatives, go to the pi until your final answer. Okay, that's what I would do. Doing it by hand, FOIL this out. 4x squared plus 12x plus 9. Take the antiderivatives of that. Plug in 3, that gives you 117. And then times 5. It's really not hard. Okay. Ditto, first thing. Okay, shh. Find the volume of solid revolution generated by rotating in a region bounded by y equals the natural log of x, y equals 1, y equals 2, and the x-axis around the x-axis. Your axis of rotation is now a vertical line and not a horizontal line, which means that you're going to need to do this dy instead of dx. Now, to help you get started, I will remind you that is a line y equals the natural log of x. Just like that.
That's very helpful.
You should know the basics of basic functions. You should know what natural log looks like. You should know what e to the x looks like. You should know what a sine curve, a tangent curve, a cosine curve, a quadratic, what they all look like. You should know what an absolute value looks like. Some of them aren't that hard. Some of them, on the other hand, are a little more complicated. You need to know what this looks like. Okay, fill in the other lines. Find your equation, your bounds. So let's finish this one up. So you have the line y equals 1, the line y equals 2. You're rotating around the y-axis, so you're going to get an object that looks something like that. Because your axis of rotation is vertical, your radius is horizontal, which means you have to do this dy. So y equals the natural log of x. That means x equals e to the y. And our radius in this case is e to the y. So my volume is the integral of pi e to the y squared dy from 1 to 2. Now you can plug that into your calculator if you were solving it by hand, but you said it does ask it for decimal answers. I actually worked it out. So you end up getting pi times, this is e to the 2y, so your antiderivative is 1/2 e to the 2y from 1 to 2, and I got pi over 2 times e to the 4th minus e squared, which when you work it out to the nearest decimal tenth, you get 74.1, or is it 1 or 2? 74.2 when you do it on your calculator. Okay, not too bad. Set up, but do not solve. The volume of the solid of revolution generated by rotating the region bounded by y equals the tangent cubed of x, y equals 1, the y-axis, and rotated around the line y equals 1. I will give you a hint. Y equals the tangent cubed looks an awful lot like y equals the tangent of x. In fact, the only difference between tangent cubed and tangent, as far as graphs goes, is the tangent cubed is a little flatter when it's at the beginning and end and near the x-axis. So it's kind of a little flatter and then goes up sharp rather than going up sharp to begin with. So it looks an awful lot like it. You should know what tangent curves look like. That's like you should know a basic sine and a basic cosine. You should know what a basic tangent curve looks like. It's important to know that. Okay? Draw the picture, label things, and then come up with your equation. Okay, let's do this. So, XY axis. This is the line. Y equals the tangent cubed of x. So it's that. The boundary is this, the y-axis, and the line y equals 1. So this is the area we are rotating. It's this is what we're spinning. What are we spinning it around? We're spinning it around the line y equals 1. So we're getting some shape that goes with that. This is our axis of rotation. How many of you said the radius was the tangent cubed of x? Because if you did, you were wrong. The tangent cubed is this distance here. That's what the distance tangent cubed of x, it's the distance from the x-axis to that curve. When I plug in x, that's my y-coordinate for that. Okay? If I want to find the radius is this here. But the tangent cubed of x doesn't give me this length. What my radius would be this distance up here. What is that distance? It's 1 minus this distance here, which is the tangent x cubed. So my radius is 1 minus tangent cubed x. The center of rotation is 1. The distance between that and the edge of what I'm rotating, that's my radius. Okay, so it's 1 minus the curve. Because the curve takes me from the x-axis up to there. So you will have to make adjustments to your radius accordingly. This is part of why drawing a picture really, really, really makes a difference. Okay. So you do that. That's your radius. You got to figure out your bounds. Okay, I'm not doing it dy, I'm still doing it dx. My axis of rotation is horizontal. Your bounds run along your axis of rotation. So my bounds are still in terms of x. This one here is easy. This one here, not so much, but it's still not that hard. I want to know what the x-coordinate is for this point. The y-coordinate is 1. How do I figure out the x-coordinate? 1 equals tangent cubed of x. Take the cube root of both sides. 1 equals the tangent of x. Where does the tangent of x equal 1? Where the sine and cosine are the same. Where does that happen? Pi over 4. So my volume is the integral from 0 to pi over 4. And I can have the pi for my rotation either in front or inside. It doesn't matter. I do both. Pi times my radius squared. 1 minus tangent cubed x squared dx. Like I said, the pi, the constant of integration, that can go inside or outside. It doesn't matter. Questions? The hard part on this one is figuring out the radius. Yeah.
1 equals tangent cubed x. How do you get from the 1 equals tangent x?
Cube root. What's the cube root of 1? What is 1 to any power? 1. So the cube root of 1 is 1. That's 1 equals the tangent. And where's the tangent 1? Where the sine and cosine have the same value, which is pi over 4.
Does putting the 1 minus in front of the tangent of 1x, is that like...
Muy importante. Because the idea is, like I said, this distance here, this is my radius. Because there's my rotation, right? I'm spinning around that. I'm going from there to the edge. I'm going from there to the edge. That's my radius. Okay. The tangent doesn't give me that length. The tangent gives me the length from here down.
But is that how you like...
So how do I find my radius? My radius is this total distance. I go down and then I go back up to the edge of the curve. So it's 1, which is that total distance, minus the tangent cubed.
So if it was y equals 2, would it just be 2?
It would be 2 minus. If I'm rotating around the line y equals 2, it's 2 minus that. Okay. So sometimes if you rotate around a line if you rotate around something other than the x or y axis, you will have an adjustment to your radius accordingly. Find your curve. Find what you're rotating around. Draw the axis of rotation. Make sure you have that label. If your axis of rotation is something other than the x or y axis, it will not be the function. It'll be something else. It'll be 1 plus or minus that function depending on whether it's above or below. If I had drawn, let's say my axis of rotation was actually below the x-axis, let's say it was -1, my radius would actually be 1 plus to the tangent cube. If I'm rotating around a line down here, it would be a different shape. It wouldn't be this shape, but it would be 1 plus that. Because it would be the distance here plus that distance to where my axis of rotation is. So you have to pay close attention to that. And that's really important. And it will be more important when we do washers next week. And when we do volumes of washers, it will be really important. Okay? Any questions?